working with Chapter 5, Section 1, looking specifically at derivatives of natural logs today. And first off, we're going to do just a quick review of the properties of natural logs, and then we'll talk about the derivatives of natural logs. So, do you remember how to do these, like finding the inverse of a function? To find an inverse, all we need to do, right, is switch up the x and the y. So I would say I've got y equals 3x minus 2. So if I switch this up, I can say x is equal to 3y minus 2. Now solve for y. And so I'd add 2 over, and then I'd follow up by division of 3, and that's going to give me x plus 2 divided by 3 is equal to y. And this would be known as the inverse function to that original. How about, do you remember how to rewrite the natural log equation into exponential form? So here I have a natural log. Remember, ln stood for natural log, and it has a base of e, so it's understood that e is the base down there. We want to write it into exponential form. So I'm going to use that knowledge about e being the base, and it's going to be base to the power will equal this argument that we were taking the natural log of. So I will have e to the 3t plus 5, that's all the power there, equals x. And that's all they ask for, is just rewrite it. Theorem 5.1 has properties of natural log functions. The natural log functions has the following properties. The domain is from 0 to infinity. And that is because I'm looking at the natural log of x. Well, if I took e to some power, I will never ever, so e to a power will reply with this value here. This value of x will never be negative. So this domain for x has to be the positive values. The range will turn out just fine. We can get range values from negative infinity up to positive infinity. What we're looking at here on this red line is the graph of e to the x. Next up, the function is continuous, and it's increasing, and it is a one-to-one function, meaning for every x there's exactly one y, and for every y there's exactly one x. Also, we can talk about the graph being concave downward, and that is for the natural log function. This would be concave down. This one here is concave up. So what I'm showing you here, and maybe you recognize it, is that we have an inverse function. Y equals e to the x is an inverse function with y equals natural log x. So there's that line, x equals y, or y equals x, and I see the mirror image over it. That is a property of inverses. If a and b are positive numbers and n is a rational number, like a fraction, then the following properties are true. And we're going through the log properties. These should be ones that you recognize. Base e. So e to what power gives me 1? E to the 0 power. So that makes the natural log of 1 equal to 0. Sorry. Natural log a times b. When I have an argument that has multiplication in it, I can break this apart into 2 natural logs using addition. Get the plus sign there. The next one I kind of think of as the power property of natural logs. I'm going to bring out the n. N can get placed out front, so I'd have n natural log of a. And remember, they've restricted already the domain so that a and b are positive values. That's why I'm not drawing absolute value signs around them. Finally, the division or the quotient property here for natural logs, it allows us to break this into 2 logs, log a minus natural log b. Good ones to remember. So rewriting these expressions as a logarithm of a single quantity. I'm going to use the power property as well as the one that had addition. So I know if it was added, if I have two natural logs that are added, this is going to come back together using multiplication. But before I bring these back together as multiplication, I'm going to deal with this coefficient up front and bring the power back up to where it once resided. Doing that, now I can express this as one single natural log. On the top, or one of the components would be x minus 3 cubed, and the other one's going to be x plus 5. And that is all within the natural logs. So probably should have that extra set of parentheses to show that both those terms get multiplied and then taken the natural log of. Letter B, let's swing the 5 back up and the 2 back up. That'll make natural log x to the 5th minus natural log y to the 2nd minus natural log of z. I see subtraction signs. Subtraction signs will correlate over to a single log using division. So now I'm going to have natural log of x to the 5th over y squared and also z. And you're probably wondering, how does she know that both of those belong down below? Well, for one, they were both subtracted. What I could do, if it makes it easier for you to see, is I could think of this as the natural log of x to the 5th minus, and pull this negative forward, right? And then I could say I've got natural log x to the 5th minus, and this would be a product property because of addition, y squared times z. And now it's kind of clear to see I've got subtraction, and that's going to lead to a quotient rule of these two items going down to the bottom. So a couple different ways to think of that one. Using the properties of logs, please expand these logs. Go ahead, give it a try. Hit pause and maybe write these 3 out and see if we match up with what we're thinking. We want to expand them, so that means I'm going to take them from one single log into 2. Well, the first thing I notice is I see division, and that's going to lead me into the property that says I can also make this equal to natural log x minus natural log 5. On this one, I'm going to swing my 5 down first, using the power property. I'll use parentheses there, 3x plus 2 over x to the 4th. And then I'm going to use, I see once again, division, so that's telling me to subtract when I make separate logs. I suppose the 1 and 5, oops, better get this out front, huh? One final thing I could do is take this 4, which is a power, and swing it down front. And if I simplify this by distributing the 5 as well to each of the logs, I believe you're going to end up with this 4 here times the 5, giving us 20 natural log x. Sorry, I just noticed I skipped that last one, didn't I? Final one will be, what I see when I look at this is multiplication. 5 times e to the 3rd. Let's write that. Natural log of 5 times e to the 3rd. Since I'm seeing times, or a product, I'm going to separate this into 2 natural logs using addition. Natural log of 5 added with natural log of e to the 3rd. Ooh, and maybe some of you are thinking, that is something special. I kind of remember this. Let's take this one more step. Power rule says we can bring down the 3, and we'd have 3 natural log e. But the natural log of e is simply 1. Why? Well, think back to the basic idea. Base to some power equals e. The power would have to be 1. And when you're doing the natural log of something, you're really finding the power, aren't you? So we know that's going to be a 1 multiplied by 3. I think you're going to end up with natural log of 5 plus a 3. Cool. So for homework, just work on the log properties, and we will not get into derivatives. It looks like I've got that saved for a different time. We'll do that as our homework for this evening, or watch the next video for the evening, and then we can work on that during class on Tuesday. So have a great day. See you later.